All right, hey everybody. We're going to do another example using trig substitution to compute an integral. So last time we came up with this little chart here, or I introduced this chart, where we have three expressions, and that if you see something in that form, then it gives you an idea for a substitution to use, and an identity that's going to possibly make that substitution work the way we want. So the idea with these is this, though. I just want to be clear. It's not a guarantee. This is another thing in our tool belt that if we see something that looks like this, we're going to try it and see if it works. Often it will, sometimes it won't, and then we try something else, right? We're gathering tools in these videos that we can use. So here's an example of this. And one of the reasons I'm doing this example in particular is because it doesn't exactly fit into one of these categories. So I've got this integral. I want the antiderivative of x divided by the square root of 4 minus 9x squared dx. And so this doesn't fit into these categories, but it is close to the first category, a squared minus x squared in the square root, right? So we see that in the denominator there. So it's not precisely what we have, but we see something like it. It's worth a shot. And so let's see if we can make some moves to help ourselves out here. So I'm going to start with the following substitution. Okay, I'm not doing the trig sub yet because we don't quite have it in this form. And I'm going to use the substitution u is equal to 3x, which means du is 3 dx, or dx is equal to 1/3 du. So let's see what this does to our integral. So that x, right? If u is equal to 3x, x is equal to 1/3 u. So I have a 1/3 u in the numerator. Notice what I have in the denominator. 9x squared is just 3x, is this quantity squared. In other words, u squared is equal to 3x squared, or 9x squared. So that 9x squared becomes a u squared, and then my dx becomes 1/3 du. Let's clean this up a little bit. There's a 1/3 and a 1/3, so I've got a 1/9 sitting out front, and then I've got u over the square root of 4 minus u squared du. Okay, and now that 4 minus u squared is exactly what we see in this first expression, right? It's 2 squared minus u squared. So it's the case where a equals 2. So let's try to just follow the rule here. So I'm going to take not x, but u equal to 2 sine theta. Excuse me. And that makes du equal to 2 cosine theta d theta. And before I make this substitution, let's just note something. Remember, when we make these substitutions, theta is between -pi/2 and pi/2, which means sine is going from -1 to 1, which means 2 sine is going from -2 to 2. Well, look at the expression we have here. Because we have a square root, 4 minus u squared, that is almost precisely the domain of this square root, right? This makes sense as long as u is between -2 and 2. Otherwise, we get negative numbers in here. The 0 is outlawed, so in this case, we'd actually be restricting the endpoints of this as well. But it's just nice to see that it covers the whole domain that we need it to cover. All right, so now let's make this substitution. So I'm going to continue down here. I've got my 1/9 out front. U becomes 2 sine theta, square root of 4 minus, so u squared will be 4 sine squared theta, and du becomes 2 cosine theta d theta. Let's go ahead and collect some constants. So the 2's can all come forward. So I'll have 4/9. I'll have sine theta I'm just going to put this cosine theta in the numerator, keep things together. Let's do a little bit of work while we're here. I can factor a 4 out of this expression inside here. Right, because remember the other thing in this chart, it tells us I might want to use the identity 1 minus sine squared is equal to cosine squared theta. And so I see that in this square root, I have that if I factor out the 4. I can then take the 4 outside of the square root, it becomes a 2, which will cancel with one of the 2's in the numerator. So let's just do all that. That all becomes 2/9. I've got sine theta, cosine theta, over the square root of 1 minus sine squared theta, theta. So now we've got 2/9 sine theta, cosine theta, and that 1 minus sine squared theta becomes cosine squared theta, d theta. Now, I think we talked about this in the last one, but it bears repeating. When you take something and square it and take its square root, you don't get the same thing back. So that's not what I meant to write. If I take the square root of a number, the square of a number, and then take its square root, I get the absolute value of that thing, right? Because if x started out as negative, when you do this, you'll get the positive. If it starts out as positive, you get the same thing back, which is precisely what the absolute value function does. However, on the interval negative pi over 2 to pi over 2, right? That was our interval. Cosine is positive or 0, although we're not using the zeros here because of the fact that we're in the denominator, which means we do get back what we started with. The absolute value does nothing to positive things. So this becomes sine theta, cosine theta, over cosine theta, d theta, and we can lose our cosines with the cancellation rule. And so now we just have a very simple antiderivative to take. The antiderivative of sine of theta is negative cosine theta, and then we want our plus c. Now, we're not quite finished, okay? Because I want this in terms of x. So let's copy our substitutions. We had used 2 substitutions. We had u equals 3x, and we had u equals 2 cosine theta, okay? So, no, sorry, 2u equals 2 sine theta was the substitution. Pardon me, that would have been easy at this point, but also incorrect. So we need to figure out how to write this cosine theta in terms of x. First, I'm going to try to figure out how to write it in terms of u. Well, let's go back to our trusty trig identities. We know that sine squared theta plus cosine squared theta equals 1. Cosine squared theta is then 1 minus sine squared theta. And cosine of theta is then going to be the square root of 1 minus sine squared theta. Okay? Again, there's a plus or minus here, except for the fact that we know cosine's positive on our intervals. So we're taking the positive square root. Well, look at this. We've got a nice expression for sine sitting right here, because I can rearrange this to get u over 2 is equal to sine theta. So that means cosine of theta is equal to 1 minus u over 2 squared. Let's clean this up a little bit. I'm going to write this as 1 minus u squared over 4. And then I'm going to factor out a 1/4. Well, this is not strictly necessary, but I'll show you why I'm doing it in just a moment. So if I factor out a 1/4, I get this. The 1/4 can come outside the square root as a 1/2, and I've got 4 minus u squared. And now finally, I'm going to use the u equals 3x substitution and write u in terms of x. So this is 4 minus 3x quantity squared, or 9x squared. Remember, and this is all equal to cosine of theta. So now my antiderivative, I'm just substituting in the expression I worked out here for cosine of theta, which I can write as negative 1/9. Oops, I forgot to put in the square root, the whole thing we just did. Equals, there's my eraser, 4 minus 9x squared plus c. And that is our antiderivative of, let's put it here, make it look complete. We started with x over the square root of 4 minus 9x squared dx. Okay, so the reason I factored out this 1/4 here was just to make it look like it did in the beginning. We had this 4 minus 9x squared in the denominator. I wanted to make it look like that. It would have been appropriate to not do that as well. It just wouldn't look as similar to the beginning. It would be the same thing. I'm not going to do it, but if you take the square root, you will see quickly that we do get, it's pretty easy to see what happens. There's a chain rule here. The square root gives us a 1/2 power and becomes negative 1/2. That's why we end up with the thing in the square root in the denominator. Then the chain rule gives us a 2 times negative 9x, which cancels with the 2 from the square root and the 9 that's sitting here to get rid of it, and we'll have this thing here. So I'll let you work that out in detail on your own, but this does indeed give us the antiderivative. Okay, that is it for this one. Thanks, everybody. See you next time.